This will work. Hopefully I can capture these in enough resolution that you can zoom in. So not optimal, nothing's optimal. It never is. So we always think all the time how to come up with optimal solutions, but they're always based on a lot of assumptions. So my assumption was I was going to have a projector on the board. So we're never quite optimal. But I want us to take a moment and think about where we're going in this class. We'll come back to this later. But I want us to think about different branches of inference. So this is a class about inference, and that's a pretty big field. That comprises everything. So that's what we want to do as statisticians, is to infer. So there's different types of statisticians, different ways of doing inferences, but I'll give you a couple methods. You can already tell that's not going to show up. Here we go. But there's different brands. Somebody tell me one.
Fiducial?
Fiducial. So that's a school of thought. That's an interesting one to start with. Who said it? So Andre knows about fiducial stats. That's interesting. So people at Carolina still study that.
Yeah.
So there's a correlation there, isn't there? So yeah, I still see some of the old guard over at UNC studying fiducial stats. We don't do it too much these days. I'll try to make a point about that as we go. What are some other brands of inference? Bayes. So there's a lot of ways to say this word. So I say Bayesian. Sometimes you'll hear people say Bayesian. And sometimes you'll hear people say a mixture of those two things. Bayesian. So we're going to assume they're all correct. I say Bayesian because I don't know of anybody named Thomas Bayes. So, but this is a person that it's named after. So we'll study a little bit about Bayes. I would assume that this class is about 20 to 25% Bayesian. We're going to touch on all different types of inference. So it's not going to be just my favorite stuff. We're going to compare. We're going to contrast. What are some other brands? Frequentism. So something to do with repetition. So that's what frequencies are. It's we're repeating something and we're counting. And there's different ways you can do that. So there's different types of frequentists. We've got to understand what this word is. And eventually, hopefully by the end of the class, we kind of understand what all of these things are. Bayesian can be an optimal frequentist. So I want to point that out right up from the beginning. Bayesian is not obligated to be a frequentist, but they could do something so if you repeat it over and over and over again, we get good answers in a similar way to other types of frequentists. There's asymptotic frequentists that kind of look at the limits. What happens is n, the number of data points in our sample, goes off to infinity. And that's a little bit different than maybe the conditional frequentist. And there's different types of frequentism. There's relative frequentism. And so it's not just one thing. Let me throw down just one more that I hear people talk about. And it's classicism. So classical stats. So I want us to take a moment, get to know each other a little bit, use our voices so that we can interact a little bit here, because that's what we're doing here. I do know from previous experience, you're reluctant to speak up with the mask. So let's just get past it. So if we do that on day one, we're going to be okay. So I kind of understand. I was weirded out about the whole thing 6 months ago, but now this is how I know what you guys look like. It's which mask you wear. So anyway, I think I can make out most of you. But let's just start here. This one people seem to know a little bit about. It's become popular. Our textbook written by Casella and Berger, George Casella was a Bayesian. He was also a lot of other things. And so, but a lot of the groundbreaking work in Bayesian stats, Casella did. So you'll see these problems get sprinkled into the book. Now, the book is ambitious. It tries to cover all these different branches, including computational statistics. And they're saying a lot of things, and sometimes they say something in a paragraph, and it's very mathematically worded, and sometimes they work through a derivation and they show you, for example, what's going on. But these different branches have different mathematical types that you would use to solve the problems. That's what makes this class hard, is that you're jumping around doing limits, figuring out what limit distributions are so you can do inferences, and then maybe you're doing something like a Bayesian would do things. Very different. You know, not too many limits there. We always condition on the data. So somebody help me out. What's a good definition for Bayes? I'll leave. Peter.
Using different pools of information.
Different pools of information. Okay, so they stratify. So maybe different pools of info. And that's kind of true. So Bayesians do that. I'd ask you to define what's a pool. Don't know. Different compartments. Can anybody else help out? Start to narrow this down. This isn't a great definition in my mind because I could probably say it about a lot of different groups. So I wouldn't consider that a distinguishing quality until you tell me exactly how to do it. So I think a lot of statisticians do that. Anybody else? We're allowed to be wrong. We're usually wrong before we're right. Well, you guys are going to have to split the difference. Danielle.
Okay. Might be wrong, so they're taking Bayes. I think the parameter of interest itself is a random variable.
Yeah, parameter of interest becomes a random variable. That's true. So parameter of interest. So usually we call this theta in this class. Is a random variable. What's a random variable? You've got all this technical nuance.
It's not fixed.
It's not fixed, okay? That's true. That's also true of any sort of function. So, not fixed. But I'll say to Jess, and she'll agree with me, is in likelihood functions, the parameter is not fixed. And it's not a random variable either. So that's not exactly nailing this down, because it doesn't distinguish against the likelihood function. I'll kind of say, here's what makes things a Bayesian to me, is they put the distribution on the parameter of interest. So I'll say they use the posterior. I'm going to just say it like that, and we'll go into mathematics later. So Bayesians use the posterior distribution. So still not a very good definition. I would say, you know, if I were at a party and somebody said, hey Scotland, I've heard this stuff about Bayes. Tell me what a Bayesian is. And I say, well, they do inferences based off of the posterior distribution. It's not going to help them. So what does that mean? So they put the probability on the parameters of interest for the unknown quantities. So I would say Bayesian's always condition on the data. So it's a conditional statement, and then their unknowns get upgraded to random variables. That's not a good party definition for people. And so you might say they put probability distribution on the unknown parameters given the observed data. And they might say, doesn't every statistician do that? And the answer is no, they don't. So we need to work on this definition. So this needs work. It needs some work. I'm going to give you this for homework. So on the schedule, I asked you to define a number of different types of statisticians. I'll repeat what the homework assignment is in a moment, but I'm going to ask you to define those. And I want you to be fairly concise and not use too much jargon or mathematics. Now that's really hard. So it's like then we get into these loosey-goosey sort of definitions. So if you go to Merriam-Webster, I think they say a Bayesian is one that uses prior information. And maybe that's where Peter was coming from. That he knows that there's a likelihood function given your data, and then there's a prior. So this is the likelihood, and this is the prior. Usually they normalize things so it integrates to 1 under whatever this curve is. And then that thing is the posterior. But to Peter's point, without going into a full Bayes lecture, there are compartments, pools of information. Maybe you have information that you already know up front. So if you're doing a meta-analysis, maybe you could build your prior based off of previously observed data that is not in the likelihood function. There's a lot of ways to do this. And if you want to know all the details I can tell you in the semester, you'll take a Bayes class. That's not this class, but we will understand at least conjugate analysis. We'll be able to do some of the simple stuff. I might even present you with MCMC, or about chain Monte Carlo. So we know that Bayesians use that, the use of algorithm. What is that? I can't tell you all this stuff in this class, but I want us to hone in on what is the distinguishing quality about these different types of statisticians. So somebody help me out with Frequentist. What does that mean? I hear people say it all the time. I ask them, I'm a statistician, are you? And they go, oh, I'm a frequentist. What kind of frequentist? So what are you doing that's frequentist per se? So, Stephen?
Probability is based on long-term behavior.
So maybe long-run averages. Long-run behavior. See, Bayesians also do that somehow. It's in there. But that would be like kind of a relative frequentist. But there's some frequency of something that you're tracking. Let me just give you a tool. Sometimes we learn better through examples, and then we can define based off of examples. Somebody tell me what a confidence interval is. You've all heard it in colloquium or somewhere. Probably had some stat class.
So confidence interval is a interval for a true parameter of interest. It's not a, like once you construct the interval, it's not a random quantity, so you have to be careful with the definition, but basically you use your data in some way and have a distributional assumption that you use to build that interval. You can only say that the procedure, like if it's a 95% confidence interval, you can say that if you did this procedure 1,000 times with similar data sets, that about 950 of them would capture the true parameter of interest, but you can't say that there's a 95% probability that these will be captures.
Yeah, I kind of like it. You know, he's been indoctrinated with all of this stuff. It's like, it's not an interval that describes the probability of the parameter being in there. It is absolutely not that, because when Anker wrote that when he was in college, his professor came over and berated him and smacked him on the knuckles and said, never explain it that way ever again. It is a probability of that random interval covering the true parameter. And that's different from the parameter being inside of the random interval. And so we have to say this right and go, I kind of understand it, maybe. So we'll try to understand what those intervals are about, maybe compare them to Bayes intervals. But again, this isn't a comprehensive Bayes class, but we want to be able to distinguish these things. What Unger said that I really liked is, say you had 1,000 of these confidence intervals. So you saw 1,000 different data sets. And then you constructed intervals based off of each one of those data sets. If you had a 95% interval, 95% of those 1,000 intervals would overlap theta. So, and if you've ever taken a Stat 101 class, you kind of remember this being true. The point is that that's a frequentist thing. I'm talking about this interval through a frequentist lens, that if I repeated the process over and over and over and over again, 95% of my intervals would cover the truth. 5% of the time, I give people intervals that don't cover the truth. And so it's really a statement about me. So the frequentism. I give 95% of my customers good answers. And that's a big hopeful. So we already know in science we don't observe that. And so we're always publishing optimistic results and trying to make our intervals narrow because it looks a little bit better. And so in reality, our intervals don't cover 95% of the time. But mathematically, if you knew the true model, so given that model, then you could set up a procedure that does this. The difficulty is that we never really know the model. So we have to be careful there. But it's a frequentist definition. So Bayesian intervals, to kind of flip the definition, talk about what confidence intervals are not. And I like that. You know, tell us what it is, tell us what it's not. So cover both sides of that definition. A Bayesian will say, with probability 95, my true parameter is inside my interval. And that's different. And it doesn't need to be frequentist. You could set up intervals in some cases that are both belief intervals, probabilities, statements about the parameter being inside of the interval, and simultaneously a confidence interval. So a Bayesian could have intervals that have that frequentist property. So we're trying to confuse things, but we're also trying to just up front say what we should be thinking about in this class. What I want you to do on your homework, and you're just going to write me a page. It's pretty short. Homework. You're going to give me definitions. For all of these brands. There's 4 of these. 1, 2, 3, 4. And there's other types of inference as well. And there's types of inference that are non-probabilistic. So like in fuzzy logic, people have tried to come up with new paradigms. So these are all probabilistic inference techniques. So your definitions, I want them to be like 4 sentences at the most. So for each one, 4 sentences. Max. Per. Type of inference. So 4 sentences here, 4 sentences there. And we'll work on those definitions throughout this class. So I'm just going to check off that you have it. I'm going to read a couple of them. And then I'm going to say something about maybe my definitions. So once you turn in yours, I'll say something about mine, but we're going to keep refining these. So if somebody asks you what a Bayesian is versus a frequentist, you got to be able to tell them something. And so let's try to practice that. This class is going to cover pretty much all of this. We won't do fiducial stats per se, but we'll at least say what the fiducialist is. Interesting stuff. Okay, anybody want to say anything about this before we move on? So a little bit of homework. I think I wrote down that that was due on Friday, February the 1st on the webpage. So due. There's a problem with this already. And I do this all the time. So, February 1st is not a Friday. So here's my rule in class. If I ever do this on the web page, you can take the later date. That's the turn-in date. So this is actually a Monday right here. The Friday comes before the Monday. The 1st is after that, and so you get the Monday if it's longer. So I'm just going to say that in class. If I ever make a mistake on dates or I say 2 different dates, you get the longer one. No big deal. So you've got a few days to work on those definitions. I'm not going to grade those too hard. So I'm just going to look at you've done up. I just want you thinking about where we're going in this class. And so dicing up all these different fields. Okay, so last time we were studying this problem. Hopefully you got a chance to look at the first 2 lectures. Logistics. Before we jump into everything. We've got 2 dates that we need. So review, sessions, and midterm 2. Let's get that part down. This is always the hardest part of the class for me. So in our review sessions, what I'm going to do is I'm either going to be in the conference room that you've seen me film from, and I'm going to set up a Zoom channel. So we'll use our Zoom link. And I'm going to go to the Slack page, and I'm going to read in the hashtag that says review session, I'm going to read all your questions. So I hope that at least 10 minutes before review session starts up, that's populated. It'll give me a moment to just kind of think through, what do I explain first to you guys? So somebody might ask for something, and there's another problem that it depends on, and somebody else asks that other problem. And so I know which order to tell you things in. So review sessions are meant for basic help, conversation, homework help, counseling, whatever you guys might need. So I'd like to do these bi-weekly, because my homeworks are due about bi-weekly, and give you an opportunity there. Normally I say we can't do this until after 5:30 because I can't get a room. So this semester is a little bit different, in that they won't let me use a classroom outside of this period. So I'd still like to stick to the after 5:30 because I can loosen up my schedule. So let's just assume this is 5:30. And what we need is, we're either going to do this on Monday, Tuesday, Wednesday, or Thursday. And if people need to budge this time, that's okay. So I kind of mentally schedule this to take 3 hours. I think on Zoom it never does. I think maybe an hour and 15 minutes is what I was seeing last semester. 1 2-hour session I did. When I do them in person, it's kind of like, okay, I've answered all your questions, and then there's a wait. So this can go on for a while. I'm willing to do it. So, but what would you guys say? You want to do this on Monday, Tuesday, Wednesday, or Thursday? There's an obvious reason I didn't put Friday down, is nobody wants to go to review session on Friday evening. So you've got some relaxing to do, or whatever you do. So let me just poll everybody. Is this time okay? All opposed, raise your hand. Yes. No strong opposition? Okay, we'd start at 5:30. And after we see one of these, we'll get into the swing of what they're all about. Sometimes I talk about history or something like that when we're talking about a problem. give you the context of the problem, why it's important, where you'll see it in your future. So I'll do more than just solve your homework for you. Hopefully there's no homework questions and they're just all extensions of the homework. Practically speaking, I know you guys are going to ask homework questions. So when you do come in, don't say that you want to see the answer to problem 2B. So write out, say something about it. You know, articulate to me maybe where the struggle is. I understand sometimes it's like, I just can't do the integral. So what step does that come up on? So there will be problems like that. There's got to be a couple hard integration problems. Okay. Who likes Monday? All in favor? 1, 2, 2.5, 3.5, 3.5. Who likes Tuesday? Okay, keep your hands up. 1, 2, 3, 4, 5, 6, 7, 8. Likes Wednesday. Hands high so I can count them. You can vote twice, it's fine with me. 1, 2, 3, 4, 5. Who likes Thursday? That's the one I like too. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there was about 9 here. Let's do a runoff.
So you should know that the homework is due on Monday. So Tuesday is gonna be 1 week, like 6 days before the homework. Thursday is the vote.
There's a point to be made there. So if homeworks are always due on Monday, I often make them due on Friday too. Sometimes I give extensions over the weekend. So I like to do that. Yeah, maybe. So it's always better for me. I don't know why. Let's just do a runoff though, real quick. Out of these two, who likes Tuesday at 5:30? 1, 2, 3, 4, 5. Going down. Who likes Thursday? I got 15 on that one. So this is the game where I can't please everybody. Any strong opposition to Thursday at 5:30? Kind of. Can you make it sometimes? Probably. So I mean, it's one of those things. It's like the bigger the class gets, the more impossible it gets. If anybody is struggling to make it and wants other hours after class, things of that nature, set up an appointment. Communicate through Slack. If you can get a couple people together, I like that too. So I can explain things simultaneously. So I'll be flexible if you can be flexible with me. So we're going to start with the Thursday at 5:30. At 5:30, so Thursday. I don't think we need to do this week. We'll start next week maybe. So I don't want you to come to me and just say, what are your definitions to these things? Let me just hear yours first, and then you're going to scribble them down. So that's an independent exercise. If you guys want to talk amongst each other about this stuff, perfect. I like that. But just write up your own thing. Don't photocopy their definition and turn it in. So that would be a violation. But if you talk to people and you have similar answers, that's all right. No big deal. Okay, midterm 2. This is going to be in April. It might help to look at a calendar. There's April.
That's 2019.
It's going to be on a Monday, Wednesday, or Friday. We're going to do it in class.
It's 2019.
Oh, yeah. Just the sort of thing I would do. Okay, so 2021. Thank goodness. 2020 is hindsight. Monday, Wednesday, or Friday? Is there anything that looks obvious? So I don't think you guys are going to be too worried about tax dating on the 15th.
We have our tentative date for our linear models final on April 8th.
On April 8th. So that knocks us out there. That's a Thursday. You might, I don't know what your personalities are. You want 2 tests in the same week? You don't like that. I have no idea. You don't like that.
Yeah.
You know, okay, she feels strong. She's like, take my head off if we have to do that. Okay, so not that week. It's fine with me. What about the following week? I don't want to make it too late because y'all have final coming up. So we want to give you enough feedback and we want to be able to differentiate final a little bit. For midterm 1, hopefully you watch the video. I'm going to give you a take home on that, and I'm going to give you a week to solve it. So lots of time for practice, lots of time to write up clean solutions. How you're going to turn them into me, email is going to work fine.
We had 2 spring break days on the 6th and 26th, just
Yeah, absolutely. So those ones are important. So we're already out on the 6th, and then the 26th knocks out that Monday. I kind of like the week in the middle there. And I kind of like either Monday or Wednesday.
The 12th or the 14th.
Say what?
The 12th or the 14th.
Yeah, I think so. Yeah, the 12th or the 14th sound pretty good to me.
What, would this be in class or is this?
Yeah, in class. So I want to motivate you.
It's only
So
50 minutes.
I want you to have that anxiety where you're like, I better just study for another 10 hours.
So it's only a 50-minute exam.
It is. So we'll see at the end of this if there's another class marching in on us. So we can change those rules. But yeah, that's a little bit of a blow. Normally I give you 2 hours in the evening. So what I really want out of the exam is you guys to study. So I'll figure out a way to make it so that the variability isn't just because I made the test too long and the time too short. So I can do different types of tests. The important bit is you study. And if we need to make corrections, we will. So I like the 14th. This will be in class. Okay, good. If anybody has strong opposition, send me a note. We'll chit chat to figure out a solution. Let me, because I can look at my video and see when this is going to happen. So I've got all the information. Okay. I'm going to get rid of that. Thank you for being flexible. And I want to come back and talk about this problem that we've been looking at. So, simple problem. Xi is distributed uniformly between 0 and theta is the parameter of interest. So we're going to try to learn that. I think I said this already. Eventually I'm going to stop writing IID over that thing. And if I don't tell you it's not IID, then it's IID. So that'll be my rule, so I don't have to write IID every single time. Independent and identically distributed is what that means. We need to go through exactly what that means soon enough. But we're going to randomly sample from a distribution. And I said what this all meant. It means that I'm going to draw data points that live between 0 and theta with PDF 1 over theta. And so this function right here, the PDF, is telling us, in terms of proportionality, how likely it is to sample a point here versus here. That's our PDF. And that's just 1 over theta. So uniform distribution. So if I build a histogram in this space, I sample a lot of times, it should look flat eventually. It's kind of a hard problem. So it has to do with theta being on the boundary. So we wrote down a number of different solutions. So I think I said possible estimators. I gave you a bunch to chew on. And I'm sure some of them you're like, where does that even come from? And that's what this class is about. Giving you methodologies so you can derive estimators and understand what their properties are, instead of just coming up with creative ways to do it. So, one estimator. They're black. I'll just call this theta hat 1. I think I said this might be the range. The range is just the maximum minus the minimum. So, and I gave that some notation, xn minus x1. So the order statistics. So I take the max order statistic and I take the min order statistic. So I might draw these values once I sample n times. Maybe my second value is here. This was my first value. My third value wound up here. The fourth thing I sampled is right there. And then maybe the fifth thing I sampled is right there. So this is x5, x4. This was x1, this was x2, and this is x3. So the order statistics are these: x1, x2, x3, x4, and x5. So we changed the notation slightly to show you that we ordered everything. And in the coming days, we're going to figure out what are the distribution of the order statistics themselves. And so it's different from the distribution of the xi's. So maybe this is a good answer. You kind of know that this is budging against theta as n goes up. And this is budging against 0. We looked at another estimator, theta 2. And this was 2 times the mid-range. This is just 2 times xn plus x1 over 2. I think I said in the video, I don't really like this estimator aesthetically. It's weird. Saying that, we did already notice this thing tends to be that thing. It's estimating theta. But this is converging to 0. x1 is converging to 0 as n gets really big, and that's converging to 0. So they're converging to the same thing. But they're not the same thing for any finite data set. Other estimators. So I think I have a Bayesian estimator. And I take this to be n plus 1 over n. And this is going to be times x, n, the maximum. And you're probably wondering, how was this derived in the first place? How did you use Bayes to get that? And I probably could have used other techniques to come up with this estimator. So I imagine maybe some frequentist has a different argument as to why this estimator is good. So we might agree on the answer, but we have different procedures. I like when that happens. That makes me feel good. We don't always see that. I'll just point out, for Bayes, there's 2 components. There's the likelihood function, and then there's the product. So it's weighted likelihood is what Bayes is. I'll be more formal about this next time. I don't want to give this whole lecture. But by the end of class, we'll be able to derive this. The prior I used for this is 1 over theta k, where this can be chosen right here to give you different properties. So don't worry about this yet. but this is called a power prior. For the example that I coded up and I ran, k was equal to 2. And that gives me the unbiased answer. I think k is equal to 3 gives us minimal MSE. And that's also coded up in my stuff. So I think, call this theta hat 3. Might be in different order than I put it in my code, but these are just alternative choices. Real quickly, what's the likelihood function? Longer.
Isn't it the product, isn't it the joint density, but treating the parameter as it's not fixed, but it's
Variable.
variable.
Yeah, it's not random, but it's variable. So Unger has it right. So I'm not going to dwell on this too much, but you might want to look this up. What's a likelihood? But he says it's the joint distribution. So maybe in the IID case, what I would do is I'd take all my fxi's, I'd have my parameter of interest in there, and I'd product these things up. This would be actual data. It would be fixed. And then you let this be variable. So it looks just like the joint sampling distribution when I write it on the whiteboard. It looks exactly the same. So if I didn't tell you what was fixed and what was variable, and I just wrote this down, you might think the thing is fixed and the xi's are random. So this would be the joint sampling density, if this was a continuous thing. But if I plugged in data into this, and then I let theta be variable, that's called the likelihood function. I will certainly go back over that. So, does anybody know what the likelihood function is for this problem?
Whatever the data.
Just as data. So, yeah, it's like this. So our likelihood function is going to be the product. I said IID stuff. So I go from 1 to n, and then my fxi's are going to be 1 over theta times the indicator function that xi is less than theta. It's also going to be greater than 0. But I don't need to say anything about 0 because it's a known value. It's guaranteed these xi's are greater than 0 if I sample from this uniform. And so we just write down what this is. So this is just I goes from 1 to n, fxi, given theta. So what fxi is, this is 1 over theta times the indicator. Xi is less than theta, less than or equal to theta. And so let me just give you what this notation means. Xi is less than or equal to theta. This is going to be equal to either a 1 or a 0. This is true if xi is less than theta. I'm thinking of this as a variable, theta. And so if I make my theta smaller than one of the xi's, that's not valid. And so the likelihood goes to 0 there and saying that's not possible. So this is if xi is greater than theta. So it turns out this function right here, the likelihood function, and I'll just give you some notation, x1 to xn. This is going to be equal to, I goes from 1 to n, 1 over theta, delta function xi less than theta. But this doesn't have anything to do with the data right here. There's no data in that. I can actually get rid of the 1 over theta. It's not the important part. And so I have a product of just the xi's being less than theta. I'm going to say this is identical to the indicator function that the maximum is less than or equal to theta. If the max is less than theta, then all the other ones are less than theta too. And so I can simplify the likelihood function. It turns out the Bayesian analysis corresponding to this answer is the one that we get when we multiply this likelihood function times this prior, and we normalize everything, and then I come up with the expected value. So that is the expected value under this model. I know that's a lot for today.
Can you repeat this one again? The rest of this?
So, I guess I was just saying that under this particular model, this is the estimator that we get when we use the expectation. So, this is going to be the expected value of theta given all of my data. Gives me that as an answer. So a lot of calculus I have to do to get that answer. So there was another answer that some people thought was interesting. Peter made a comment about this on the Slack page. There was a least squares estimator that I gave, and it's not very good. So this came from this argument that minimizes over theta the sum I goes from 1 to n, the order statistics minus I over n theta squared. So I called this a least squares estimator. And it's the answer that's found by solving this problem. And so the R minimizer is not the minimum of this, but it's the theta value that minimizes this. And some of you might know how to solve this problem already. This looks just like a regression problem to me. And so I think next time we're going to come back, I'll discuss this solution, then we'll run some code, see how these estimators compare to each other, have a small discussion about that, and then I'm going to get into exchangeability versus independence. So, which relates to an upcoming homework problem that I wrote out on the page. And so, I want to get into characteristics of data. And then, after that, I'm going to show you all about the bootstrap and have you exploit some of this random sampling stuff. So, that'll be our sequence for the week. And then, we'll move on from there. So, I think we need to get into the central limit theorem. We need to get into the delta method. So, those are all upcoming. If you guys want a glimpse into the class, all of my videos from last year's class are on the Lehman Lectures page. So you can go to the corresponding date, and that should be very similar to the lecture that I'm going to give. So if you want a different view of the class, you can also watch it for that purpose. I want to point out our TA in the class, that's Mohammed Salam. So he's going to make himself available to you. And one of the things Mohammed's going to help me do is keep up with the Slack page. So I'll send you a link to it, and he can try to answer some of your questions. I'll try to answer. He'll be available for some Zoom session in the future, probably every 2 weeks. He'll jump on if you want to talk to him about his grading or his perspective on anything. But other than that, he's just going to help me grade the homeworks. And I'll be in charge of all of your exams. So that's the great thing. Okay, sorry for running over. I think that's everything for now. We'll come back starting up with that, and then we'll get into the book. Start uncovering the book. Thanks, you guys.